Trees are non-linear data structures in which nodes are connected by edges. Each tree has root nodes that serve as the parent node as well as left and right child nodes. In this course, we will learn about trees with the implementation of concepts in Python programming. Concepts like binary tree and binary search tree, along with the algorithms behind its creation and implementation, will be discussed, and we will also discuss the three different traversal algorithms for the binary search tree. So put on your thinking hats and let's get started with this session on trees in Python. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.
Binary tree. Now let's talk about what is binary tree. So it is a hierarchical data structure. As we have seen in earlier data structures like arrays, linked lists, stacks, and queues. All of these data structures were linear data structures. But when you talk about tree, is a hierarchical data structure. That means it can have one or more than one children. Doesn't have to be explicitly two children. But when you talk about binary tree, therein you can have at most two children. That means if this is the node, and then it can have at most two children, or if this is a node, it can have either left child or the right child, or it can have no children at all. Okay, so this is a binary tree, and now this is known as the root of the tree. That means the first node is known as the root of the tree, and you cannot access elements or these nodes directly. Okay, so now this is the whole structure of a binary tree. Now there are some common traversals, right? How we can traverse through all these nodes. So one of the common traversal is pre-order, wherein you always, whenever you are on this node, you always print this node first. What is the value of this node? Then you go on to the left side and do the same. Then again you go on to the left side, then do the same. Print, go on the left side, print, go on the left side, and so on. Unless and until there is no left, then what you do is print that thing. Okay. Then after that, you will go on the right side. So pre-order follows print first, then go on to the left, then go on to the right. Similarly, post is saying that whatever is you have, print it at the last. So go on the left, go on the right, print at last. And in order says left, print, and right. So these are all traversals. We will also see one by one how we can implement it, and how we will also see examples based on these traversals. Now let's talk about the applications. If you have seen the file hierarchy system, wherein we have the root folder, and inside that root folder we have subfolders like music, and we have bin, we have files, we have program files, and all those things, right? So it is a kind of a hierarchical data structures, right? And explicitly here we are not talking about binary tree but generalized tree. Now, if you have binary tree, it has multiple variations, right? If you talk about this binary tree, so here you always have either the left child or the right child. When you talk about BST, the childs are inserted in the tree in such a way that on the left side it will be always less than the root, and on the right side it will be always greater than the root. So this is a variation. It is known as BST. So you have aerial tree wherein you don't exceed the height more than 2. So that is one more variation. Then we have red black trees. So these are all variations of binary tree.
So after knowing what is binary tree in theoretical part, let's quickly implement the binary tree in practicality on Google Colab in Python. So before doing that process, so let's learn what are the different functions we are going to perform in a binary tree concept. It's generally by default, everyone will start learning with in-order traversal, pre-order traversal, and post-order traversal. So I'll quickly brief you what is in-order, pre-order, and post-order, and then we shall go to implementation part, right? So let me give you a brief explanation over this. First, we'll start with what is binary tree, right? I'm taking a simple example, nothing related to coding or anything, just a simple example. So binary tree in the sense, it should have at least one node and two different subnodes. I call it as left and right sides, right? It should have one data item. I'm putting it to 1 here, and it should also have left child and it should have the right child. So again, I'm trying to put 2 here, I'm putting 3 here, and extending with 4. So we'll be working and understanding with this simple example how does binary tree will work. So the first thing you have to know, I'm talking about in order. So what is in order here? There is a simple basic rule which you can remember. When you traverse throughout the nodes which you have in a binary tree, you have to start from the left, visit root, and then right. So I'm writing it here for you. So left first, root next, and then the right node, right side node. Okay. Then we have the next one, pre-order. How does this pre-order will work? It has the same rule, but in a shuffled manner. First you are visiting the root, then you are visiting left side of the tree, and then you are going towards the right side. Hope that's clear, right? And the last one which is left is post order. So what is post order? Again, you have a shuffled way of this 3 combination only. The first thing is it will go to left. That means left side of the particular diagram or the binary tree which you have taken, and then it will go to the right. After that, it will go to root. So this is the basic things you have to know on these 3 functions or operations which you do it generally in binary tree. So in order, pre-order, and post order. So let's quickly start with in order, right? So in order, it says we have to visit to the left first, then go towards the root, and then come back to right. So I'm implementing the same. So here, what is the leftmost node we have for this particular example? Simple example we have taken. So that is 4, if you could see, right? So this is the leftmost, and this is the rightmost, and this is the root, just for reference, right? So at the left, what do you have? 4. So for in order, I'm writing it here as well. So in order, you will put up 4 as the first element because the rule says you have to go towards the left of the binary tree. Then after 4, what do you have? This direction. You have 2. You have to first complete the left side part, then you have to go to the root. And next, on the way, what do you find? You find root. So what is the number in the root? Is 1. And then after coming back towards right side, so what is the number we have? We have 3. So this is how in order will work. So hope that's clear. We are starting from left, we are going towards the root, and we are coming back towards the right side. So again, how do you do it for pre-order? The next one. So what does pre-order say? You have to first visit root, then go to the left, and then go to right. So I'm going to root here in the same diagram. I'm drawing one more here for your reference. So this is 2, again this will be 4, and this is 3. Hope that's clear. So we are working for pre-order here. It says we have to go for root first. So what is the element in the node? That is 1. Okay. So next, it says you have to go towards the left. So what is there in the left? This side, you have 2 first and then 4. So what I'm writing, it's 2 here and 4 next. Then you have to visit right side. So at right side, you have 3. So this is how pre-order traversal will work in binary tree. So quickly, we shall see the last one, that is post order. Right. Post order, as per the rules, what does it say? We have to go towards the left first, then right, and then root at the last. So writing down a simple diagram again here for avoiding the confusion. For this is 3. Okay, so we are doing that. Left side, what do you have now? We have 4. Again, continuing, you have towards the right side 3. Right. After having 3, what do you have? You have to go to root. So what does it say? You have to first complete whatever there in the left. So what we have left out here? We have left the 2 because it is also on the left side. So what we'll do here, right? We'll try to put up this 2 here, finish it off. That is 4, 2, 3, and then you have to go to 1. So first what did I do? I went to the left part, that is 4. So after that, you have 2, and then you have to go to right and then root. So this is the root. We can't go there until unless we finish towards the right side. Towards the right side we had 3, and then we went to root back. So that makes 4, 2, 3, 1 as a post order. Hope this was clear for you. And now let's quickly hop into the coding part and check out the same elements, the same functions. How does that work? So what is happening here is the same example I've taken in a coding format. That is where I'm taking the 4 different nodes, that is 1, 2, 3, 4, and applying all the 3 functions we have. That is in order, post order, and pre-order with the same way of working but in a coding manner. So what has happened here? The first, if you could see, they have put up a class that is node, right? So after creating a class node, we have to initialize the values. Val is nothing but root, right, and left. So we have to have one single root node, and we have to have left and right for the same root. So then we'll create some functions for traversing towards pre-order, traversal towards in order, traversal towards post order. To make it clear and precise enough, I have kept related name to the functions and classes here. So what happens here is we'll be using the functions called pre-order, post-order, and in-order. So first it will visit the nodes accordingly as I told you. So first for pre-order it will go to root, left, right, and for in-order it will go for left, root, right, and again for post-order it will go for left, right, and root. So let's check out how does this program work in the manner. So here you could see I've used the left and right accordingly. So as per the rules I have told you, that has been used here as well. So let me quickly run the program for you and check out what is the output we get. Right, if you could see here, pre-order, we got it as 1, 2, 4, 3. The reason is because it is going from root, left, and right. And for in order, we are going with left, root, and right. So left side we had 4, 2, and again 1 was the root node and 3 was at the right. So left, root, and right. If you go for post order traversal, then it will start from left, right, and root. So leftmost was 4, 2, and it went to right. Right side was 3, and root is 1. So this is how the traversal will work in binary tree in Python.
Now let's talk about advantages and disadvantages of binary tree. If you talk about advantages, we can represent data with some relationship, right? So this is the root node, or this is the parent node, and this is the child node. So that relationship, parent-child relationship, is always there. And while you are inserting or searching an element or a node in a binary tree, it is much more efficient as compared to other data structures which we have seen. Now, if you talk about disadvantages, if you want to sort this binary tree, it is much more difficult, right? Because we can either go on the left side. This can be a tree, that means this is a left skew tree, or this can be the scenario wherein we have all the elements on the right side of the node. So this can be another scenario wherein we have this right skewed binary tree. So sorting is difficult and it is not much flexible, right? If you talk about this binary tree, we always have either the 2 children or 1 children or no children. There is no flexibility in terms of how you want to store it. Can we store another node on the with this root node. No, that is not the case, right? And we don't follow any restrictions like, okay, we always find this node. That is, if this is a root node, we always find an element which is less than this node on the left side or on the right side. That is the greater element. So that flexibility is not there. Binary search tree. Now, what is binary search tree? So, binary tree is an additional restriction, right? This BST is nothing but the additional restriction on binary tree. Like we have already seen the binary tree wherein at most we can have two children, right? It can be on the left side or it can be on the right side. Now, what are the restrictions on this tree? So, the restrictions are that the data, that is, let's suppose this is 5 and these are another two nodes. Now, the restriction is that if this is a root node, then you always will have the element that is less than your root node. So you can have 4, 3, 2, 1 on these sides, but you cannot have 6 on the left side. Similarly, you can have 6, 7, 8, 9, and so on. On the right hand side, you cannot have 1, 2, 3 on the right hand side. So these are the two restrictions that are there in binary search tree. Now, if you talk about insertion, deletion, and while you are searching the element in the binary search tree, it is much more efficient as compared to binary tree, because we can obviously, when we are trying to search for an element, we can obviously, if let's suppose we are searching for 8, so will it make sense to go on the left hand side? No, we can easily neglect this part. Similarly, we can do it on the rest of the elements. This is one scenario wherein searching is much more efficient than binary tree, because in binary tree we cannot neglect any elements, or we cannot say, okay, no, we cannot find an element on this portion, on that portion. Similarly, when we are inserting, now, if the element is greater than 8, so we can easily, in this scenario, right, we can easily go on the right hand side rather than searching where we want to insert it. And similarly, when we are deleting, a little bit of ordering is done in order to get the exact same situation, wherein your root is less than the right hand side elements and wherein your root is greater than the left hand side elements. So that scenario is there in the binary search tree. Now let's talk about the application. It is suitable for applications which require sorted hierarchical data. Let's suppose you have some data and you want to store them in such a way that always you want your elements that are greater than the root on the left, on the right hand side, right? You want them on the right hand side, and for the elements which are less than this root, you want them on the right hand side. Okay, so that you can easily neglect. Okay, you can now, let's suppose, not, if you don't want this scenario wherein you are just dealing with the greater than or the less than, you can have a similar kind of a situation wherein you are saying that, okay, on this side I will always have some files that are related to coding. Okay, let's say an example, and in this I will always have files which are related to entertainment. So you can do that so that you can easily neglect these files, because these are always going to be your coding files, and these are always going to be your your entertainment files. So wherever you require sorting, right, or you want your data to be in such a manner that it is easy for you to find, insert, and delete. So therein your binary search tree comes into picture.
After learning what is binary search tree, right, we have to implement that particular topic here in Python on Google Colab. So before that, let's understand what are the different function you'll see in binary search tree. So it is very basic function, that is insert, search, and delete. So before going to these functions, I need to let you know that how do you draw a binary search tree? You have a specific condition to be followed in order to have a binary search tree. So number one, you have to have the root node should be always greater. Whatever the subnodes which is lesser than the root node will be towards the left side, and if it is greater than the root node, it will be on the right side. You have to consider these two conditions before writing binary search tree, right? So I'll just give you a simple example of a binary search tree keeping these conditions in point. The first condition I told you is the root node should be taken into consideration. Whatever the root node is, for example, the root node is 10. Okay, anything below 10, it should come towards the left side of the root node. Anything above 10, 11, 12, 13 and so on, it should come towards the right side. So whatever it is greater should come here towards the right. What is lesser should come towards the left side. So keeping this into consideration, 10 is the root node I'm taking, and anything you want to add on, right? So I'm adding 5. When you are adding lesser than the root node, that should be towards the left side. And if you are adding anything greater than to the root node, that should be towards the right side. So I'm adding 12 here. Then after that, what you have to do is, if you want to continue to the next level, right, you have to follow the same condition. For now, just for reference, 5 is the root node. Anything lesser than 5 should be towards the left side. Anything greater than 5 should be towards the right side, right? Again, if you take 7 into consideration, right, as a root node, anything towards the left side will be having the lesser value. You can keep it as 6. Anything towards the right side will be having the greater value. You can keep it as 8. So this is how particular BST tree will work. So this is a simple example for binary search tree. So let's understand how does the searching will happen with the help of a pseudocode and proceeding with insert and then delete, right? So let's see search operation first. So what happens in search? The first thing is root node should be considered. If root node is equal to null, it is not having any value, then we will be returning null. Okay. If the same thing again, number or the value or the data, I'm taking number here, whatever the user input is, right? If the number which is given is equal to root, the values of root and the input number is same, then you have to return root only. Okay. The next condition, if number is less than root, as I told you, whatever it is less than root value, the number should go to the left side of the tree. So what do you write? And you can write it as return search. Search will traverse towards the left side. Any element you are finding over a tree, right? You are finding, for example, for number 4, right? So in a tree here, like this, anything like this, say you have different values here. I'm not writing values as of now. So the 4 is situated here. So what does it say? It goes in comparison. First, it will search for root value. Is it equal? Is it null? No. Then it will search whether it is lesser. Then the next thing which it has to search is whether it is greater. If the number is greater than the root value, right, then it has to go to the right side of the tree. Here it is left side and it has to go to right side if you want to search anything. So that is how a simple pseudocode presents here. How do you search an element inside a binary search tree? So the next part which you have to keep in consideration is how do you insert element? Again, the searching follows the same manner. Likewise, the insertion will also follow some similar manner. So in order to insert anything inside to BST, that is binary search tree, what do you do? First, you have to check for the condition again. If node is equal to null, right? If node is equal to null, and then it will return whatever the data it is as it is. If, again, whatever the data which is given, right, by the user is lesser than node, then it will go towards the left side of it. If there's one more condition, the data or the value which is given by the user is greater than the node value, then what it will do, it goes towards the right side and we insert element accordingly as per the conditions it is satisfying, right? So this is about search and insertion. So coming back to deletion, right? Let's see how do you delete an element from the binary search tree. Deleting has three different cases to be considered. Case 1. Okay. Say for example, you have a tree here which is having certain value, right? I'm just giving a simple example. This is 8. Again, it has to be less. Whatever it is less will be here. Whatever it is greater than will be here. So if you're taking this as an example, right? The case 1. If you want to delete 9, okay? What it is, the case 1 states that directly delete. Need not do anything. Go to that node. If you want to delete 9, get it back and delete. Right. Case 2. You have one more condition to consider. So we have to replace something. We have to replace the node with its child. We have to replace the node with its child, whatever it is there accordingly. Say for example, if you want to delete 8, you have to replace 8 with 9 or 6. I think you have to use in order method in order to find which one you have to replace, because 8 has 2 children. Coming up to the third case. Particularly, we have to follow in order method, right? So in order traversal should be followed, and we have to check accordingly which one to replace and what to delete, right? Without replacement, we cannot delete and leave that particular node empty. So these are the three cases you have in order to delete an element from a binary search tree. So let's quickly see how do you implement this particular code on Google Colab. Now let's implement the same BST functions in Python on Google Colab. So the first thing which you have to do is you have to initialize a class. So I'm initializing a class called node here, and I'm considering three different elements. One is key. Key is nothing but root, and left and right for the particular tree. And next I'm considering one function, because I told you we'll be using in order to delete something or insert an element, right? So in order function will be used. What is the rules of in order? It should be left, root and right side. So first it has to consider the left side, then it has to go to the root, and then it has to go to the right side of the tree. And then again, in order to insert a node inside the tree, what are the different things you have to consider? You have to consider whether it is null or is it equal to the root node. And you should also consider if the node which you have taken or the value which you have taken is greater than or lesser than as well. If it is greater than, it is going to the left side of the tree. If it is lesser than, obviously it is going to right side, which is not mentioned here. Only one particular condition is taken, that is which is lesser than. If it is lesser than, and it is going for left side. If it is greater than, it is going for right side. So then you have again in order successor defined. That means what happens if you want to replace something, right? You have to know the successor of it. You have to know the child node of that particular node. So in order to find that, we'll be using this particular function. And next, in order to know the leftmost node, we'll be using this particular function, that is current, whatever the position is for the node, how it is traveling towards the left side. So current position, from there we'll be considering the left side of the node. If not, we'll not. If it is not having any node towards the left side of that particular node, right? So we'll not consider that as well. Then deleting a node is done. So what do you do? Deletion, as I told you, you had three different types of cases of deletion. So here we are considering with the help of in order, how do you delete an node, right? So it will be compared. First it will be seen whether it is null or not null. If it is not, then it will go inside the next condition, whether it is checking if the key is, that is the value, root is lesser than the node which you have given. So if it is lesser than, then deletion to takes place towards the left side. If it is greater than, it will go towards the right side. So likewise, it will follow the rules until unless it will delete an element by using in order. So these are the different inputs we have for it. So this is the tree generally. So it starts from 9, 4, 2 and so on and ends with 5. So considering the image of what I thought you, right? How do you write it? Considering the root node, anything towards lesser than the root node towards the left side, anything towards greater than the root node towards the right side. So this, considering this factor, we'll give the input to the program. So quickly, if we run this program, let's check out how does it display. So in order traversal, how it happens, it will go from 2 to 4, again 5, 7, 8, and so on up to 15. If you want to delete something, what you want to delete, have to delete 11. So where is 11? 11 is, like, 11 is having a successor of 15. So what does it do? 11 eliminates, in the place of 11, 15 will be there. So we'll replace with the help of in order method. What is the flow of in order? That is left, root, and right. So considering this factor, it will give you the deletion process and replacement for that particular deleted node as well. So that's about binary search tree.
Now let's talk about advantages and disadvantages of binary tree. If you talk about advantages, we can represent data with some relationship, right? So this is the root node, or this is the parent node, and this is the child node. So that relationship, parent-child relationship, is always there. And while you are inserting or searching an element or a node in a binary tree, it is much more efficient as compared to other data structures which we have seen. Now, if you talk about disadvantages, if you want to sort this binary tree, it is much more difficult, right? Because we can either go on the left side. This can be a tree, that means this is a left skew tree, or this can be the scenario wherein we have all the elements on the right side of the node. So this can be another scenario wherein we have this right skewed binary tree. So sorting is difficult and it is not much flexible, right? If you talk about this binary tree, we always have either the two children or one children or no children. There is no flexibility in terms of how you want to store it. Can we store another node on the with this root node? No, that is not the case, right? And we don't follow any restrictions like, okay, we always find this node. That is, if this is a root node, we always find an element which is less than this node on the left side or on the right side. That is the greater element. So that flexibility is not there.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.